What we're going to do here is look at how we can use Python to solve differential equations symbolically. And so that means actually getting an expression for the equation. Python has a lot of great tools for solving equations numerically, which a lot of the time is all you need to do. But when doing mathematics, sometimes, and it's important to be able to do so, we want to solve our differential equations exactly and analytically. So that's what we're going to do here. So we have that a container has volume V, and the rate of change of that container, so the rate of change of that volume, pardon me, is proportional to E of t. So when we say proportional, we mean that it's some multiplication of e to the minus t. I think I said E of t, e to the minus t, where t is time. We've then got some other information. Initially, the container is empty, so when v of 0 is going to be 0, and v of 3 is going to be 15. So that'll probably be useful to be able to get to at some point get a more specific solution. So we're going to go ahead and solve that. And so the very first thing we're going to do is import Sympy, if I can spell it correctly, Sympy as sim. And the first thing we're going to do is create all these things that we're going to be using. So we need these objects to be able to do them. So the first thing we'll do, we'll go ahead and create t, which is going to be a symbol t. We're going to create k, and there's no k specifically written out in here, so I could choose whatever letter I want. But k is what we're going to use to write down that v is proportional to e to the minus t. So we're going to use the variable k to express that. And then the final thing that we need, which might be new if you've used Sympy before, is not a function, not a symbol, but a function. So we're going to write down that v is a symbolic function. We don't have to say it's a function of what or where it goes to or where it comes from, the image in the domain, but we just need to say there is this function. And so the very first thing we need to do is write down our differential equation. So we're going to write down the left-hand side of our equation, and the left-hand side of our equation is going to be essentially this part here, that the rate of v. So that is the derivative of v of t with respect to t. If I just take a look at that left-hand side, you can see it understands this concept of a derivative of v of t. I'm going to go ahead and write down the right-hand side, and the right-hand side is going to be the proportional to e of t part. So I'm going to say that's k times sim.x of minus t. If we take a look at that right-hand side, we've got that right-hand side. At which point we can write down our differential equation to be sim.eq, left-hand side equals left-hand side, and right-hand side equals right-hand side. I'm using keyword arguments here. And there's our differential equation. And essentially, that is that first sentence, that a container has volume V of liquid, which is poured in at a rate proportional to e to the minus t. That's what that says there. So what we can do with Sympy is write sim.dsolve. So this is the differential equation solver. And if we wanted to, we could go ahead and get the help for that. We see the particular signature. And we can see solves any supported kind of ordinary differential equation and system of ordinary differential equations. So I'll mention that a little bit more at the end, but here we just have a single differential equation. So I want to solve this differential equation with respect to v of t. And note the v of t is important because I could say I want my equation to be an equation of v of k, for example, but I'm specifically saying k is some constant, and what I'm solving for is v of t. So if I go ahead and run that, you see that I get v of t is equal to some constant minus k times e to the minus t. And so what I've got now is a whole family of functions that obey this first sentence, right? A whole family of functions that give me a volume of liquid that is poured in at a rate proportional to e to the minus t, all right? But we have this extra information. We have these two extra conditions, okay? And what I'm going to do is I'm going to go condition equals a curly brackets for a Python dictionary, And I'm going to write that v of 0, oops, if I can spell 0 correctly, is 0, okay? And now I can write sim dot dsolve the differential equation v of t and ICS, which is just a short for initial conditions, be this condition. I'm going to want to keep this, so I'm going to go ahead and call that my particular solution. And now if I go ahead and solve that, and if I go ahead and take a look at that, we see that v of t is equal to k minus k e to the minus t. And indeed, we can just check that if I put 0 in there, e to the minus 0 is 1, I get k minus k, so I get 0. But we also have this extra condition that is a condition on k. The initial conditions in the dsolver can only be used to check conditions on t, which is that a way of getting rid of the constant. So let's go ahead and write out our last condition, which is our equation, which is that, and the left-hand side of this equation is that the particular solution's right-hand side, so k minus k times e to the minus t, that right-hand side, when I substitute t equals 3 in it, what I want the right-hand side of my new equation to be is 15. Let's go ahead and take a look at that. We've indeed got, when I substitute t equals 3 into the right-hand side of the particular solution, which is this part, I get 15. And so we can go ahead and go sim.solve set that equation for k. That doesn't quite look like what we're expected to show. So let's see what happens if I do a sim.simplify on this. Minus 15 e3, 1 minus e to the 3. That's the value of k times 1 minus e to the minus t, which is indeed what we have here. Okay. So now what we can do is the last part of the equation, which is obtain the limit as t goes to infinity of v of t. In other words, what's going to happen as time goes on and we keep pouring. We can write down that the limit is sim.limit, and now I'm going to write out everything again. Actually, let me break this up a little bit. I'll go ahead and say my actual expression I'm taking the limit of is going to be minus 15 times sim.x of 3 divided by 1 minus sim.x of 3, and I need to multiply that by 1 minus sim.x of minus t. Okay, so that's this expression with k being put in there. I'm factoring out the k. It's just k times 1 minus e to minus t, and we've got everything in there. And so I want to know what happens to that expression as we keep on pouring, and keeping in mind that the rate is proportional to the e to the minus t. So as t goes on, there's going to be less and less liquid going in. So we can do sim.limit, the limit of the expression as a function of t when t goes to infinity. And we get minus 15 e to the minus 3, like that. Now, that's a number. I'm not entirely sure what that number is. So let's go ahead and save that in there, write out the limit. And if I just convert that to a float, I get that the volume is 15.8, essentially over time. And so, yeah, so really the main things to keep track of here is we've got this dsolve tool, and the dsolve tool takes a differential equation and the functions and variables you're solving that differential equation for. You can also pass a condition to that differential equation solver using the ICS parameter. and that condition must just be a float. A dictionary mapping of function calls to variables. This is all taken from the Python for Mathematics text here, and this is essentially me walking through the tutorial. There's some how-tos that might be of interest. There's some exercises in there as well. And the other thing that might be of interest in the further information section is how do you solve a system of differential equations? So if you have a system of differential equations like this, how do you solve that? And so dsolve works in the same way, where you can pass in the system of differential equations, like so. Okay. And I have mentioned at the start that Python has some excellent tools for solving differential equations numerically, and you can see how to do that in this how-to section if you're interested, where you actually don't get a function, but you get the values of that function there. And I use an example that might be of interest.